Hi, my name is Kaveh Fathian, and this is a presentation on the paper titled Distributed Formation Control under Arbitrarily Changing Topology, which was presented at the 2017 American Control Conference in Seattle. This is a work in collaboration with Professors Dimitri Rachinsky, Tyler Summers, Mark Spong, and Nick Gans at the University of Texas at Dallas. The objective of this talk is to design a distributed control law for a group of robots, vehicle, or general agents such that they achieve a given desired formation under an arbitrarily changing topology. Applications of formation control are in unmanned ground, aerial, and underwater vehicles, automated highway systems, and cooperative robot manipulations, to mention a few. And the relevant work on formation control is quite vast. Here I've only mentioned a few work that I think is most closely related to the topic of this talk. The first three consider topologies that are fixed, and the last work by Han, Lin, and Fu consider topologies that are switching with a dual time constraint. Here we assume that the topology can switch as fast as we want, and there is no need to have a dual time constraint. So here's an example. We have 6 sphere robots starting from a random initial position on the plane, and under the control law, which we're about to talk about in this presentation, they achieve this desired configuration, which we defined it to be as a triangle. This is a low-cost platform that we're developing for formation control or other multi-agent algorithms in MATLAB and ROS. This platform will be made available at the link that you can see here. Also at this link you can find the code and simulations for the formation control, and you can download it, and it's all free. The assumptions that we have in this work are not to restrict the problem, but we're actually seek to solve a very general class of problems under these assumptions. For example, we distinguish between agents. We care which agent goes where. So if this is a formation, and if I swap robots 1 and 2, then that will represent a different formation. If you do not want to distinguish the agents, what you can do is to randomly assign tags to the agents and run this control law, and you achieve the formation. Therefore, this is slightly more general than the case that you don't distinguish the agents. As I mentioned, the topology between the agents can change arbitrarily. Of course, this must be a feasible topology, and the feasibility of topologies has been studied before. They're known as two-rooted graphs. All we need to achieve the formation is local relative position measurements, and by that I mean if this is an agent, it needs to sense the XY position of its neighbors in its local coordinate frame. There is no need to have global position information such as GPS sensor data. Furthermore, these local coordinate frames do not need to be aligned. There is no need to have a common orientation or heading. And lastly, the agents can achieve the desired formation without any need to communicate among themselves. So before we can talk about the main contribution of this work, we need to go through some preliminaries, and this is based on the complex Laplacian work by Lin et al. Here we consider agents which with single integrator dynamics x dot equal u, where x is the xy position of agent in its local coordinate frame, and u is the control law that we design in order to achieve the desired formation. Notice that this model can be extended to higher order models. Can be extended for non-holonomic systems, as you saw in the example of a sphere robots. So the most general linear control law that we can pick for U must have this form, where we measure the relative position of neighbors in the local coordinate frames. So this is xjl. And then we multiply that by a 2 by 2 gain matrix A, and use that as use that summation as the control law. So these A gain matrices are have 4 elements, A, B, C, D, and this is what we design in order to achieve the desired configuration. If we use that general linear control law for the agents, and then we write down after some coordinate transformation the dynamics in a global or common coordinate frame, we derive this dynamics, which as we can see depends on the relative angle between the local coordinate frames and this common coordinate frame in terms of these rotation matrices of theta I. So this means that in general the dynamics depend on the angles that local coordinate frames make with each other. However, since we are designing those gain matrices A's, if we pick them such that they commute with these rotation matrices, then we can swap A and R, and then R and R inverse will cancel, and what we get is this dynamic, which is completely independent of the relative rotations between the local coordinate frames and this global frame. So this means that we can go ahead and do all the design in this unknown global or common coordinate frame, find those set of gains, and then we will go back and apply this set of gains in the local coordinate frames of the robots. We get exactly the same behavior and dynamics that we see during the design. So everything can be implemented locally. Matrices that commute with 2x2 rotation matrices must have this form, where now instead of having 4 degrees of freedom A, B, C, D, we are limited to 2 degrees of freedom. We have A's on the diagonal and negative B and B and off diagonal. And by constraining this, the gains to this form and writing down all the equations and stacking everything into a matrix vector representation, we get this simple linear system model x dot ax for the dynamics, where x is the aggregate position vector of the agents and A is the aggregate gain matrix with block Laplacian structure. And by that I mean that these 2x2 diagonal blocks are negative sum of the rest of the blocks on that row. So here I have an example that hopefully illustrates the things better. So suppose we are given 3 agents with this desired formation, which is a right triangle with leg lengths of 3 and 4. And this is the sensing topology shown with these edges. So it means that 1 can sense 2 and 3 and vice versa. And suppose that for now we are giving this set of gains. What we're going to do later is to design them, but for now we assume that these gains are given to us, as you can see here. And what agent 1 does, it senses the relative position of agent 2, multiply that by this matrix A12, and then similarly measures the relative position of agent 3 in this local coordinate frames, multiply that xy coordinates by A13, then sum those two vectors and then moves along that direction, the resulting direction in its local coordinate frame. So that's the geometric interpretation of the control law. And this is the aggregate state matrix that you can see. A12 is here, A13 is here, and the block and the diagonal block consists of negative sum of these two blocks on that row. Now notice that if I multiply a vector of 1s into A, I get 0. And if I multiply a vector of negative 1, 1, negative 1, 1, so on, which I call 1 bar into A, I get again 0. This shows that 1 and 1 bar are in the null space of A. And this has nothing to do with the values of the gains. It comes from the block Laplacian structure of the A that this property holds. Now let's define via an arbitrary embedding of the desired formation a desired vector x star. And by that I mean choose a coordinate frame anywhere that you want, and then read the xy position of agents 1, 2, and 3 at their desired configuration in that coordinate frame. So here for simplicity we've chosen this coordinate frame where agent 1 is at the origin, so it's at position 0, 0. Agent 2 is at 4, 0, and agent 3 is at 4, 3. And if we stack them all, this defines a vector x star. And we also define a vector x bar star by rotating these coordinates 90 degrees, or simply multiplying them by this matrix. So 0, 0 is mapped to 0, 0, 4, 0 is mapped to 0, 4, and 4, 3 is mapped to negative 3, 4. Now notice that ax star and ax bar star are 0. This holds because of the values of the gains. They were designed such that this property holds, and therefore x star and x bar star are in the null space of A. So we observed that these 4 vectors formed a basis for the kernel or null space of A, and eigenvalues of A are 4 zeros associated to these 4 eigenvectors and 2 negative 3s. So we have the lemma that if non-zero eigenvalues of A, in that example those two negative 3's, have negative real parts, then all trajectories of system x dot ax converge exponentially to the kernel of A. So this means that starting from a random initial position on that plane, under that proposed dynamics and those set of gains, the agents converge to some final state, which is a linear combination of these four vectors. And that's nothing but the desired formation up to some scale factor, rotation, and translation on the plane, and this is exactly what we want. So here, a simple illustration that I've shown here, you can end up possibly at any one of these configurations, and this is what we want to get. So now let's talk about the main contribution of this work, and that's to show how we design those gains in order to achieve that formation. And we first start with the static topologies, and then we extend the work to dynamic topologies. So this is done in 4 steps. At step 1, using an embedding of the desired formation, we define the vectors x star, x bar star, and then we form this matrix N from those 4 vectors. At step 2, we find SVD, or single value decomposition of N. Let's say it's U S V transpose. At step 3, we define Q as the last 2n minus 4 columns of U. So if this is U from SVD, Q bar is the matrix consisting of the first 4 columns, and Q is the remaining part. And lastly, we define A bar as Q transpose AQ, and A bar has 4 dimensions less compared to A. So if A is a 2n by 2n matrix, A bar will be a 2n minus 4 by 2n minus 4. And what's special about A bar is that A and A bar have the same set of non-zero eigenvalues. So if we find the gains or design them such that A bar is a stable matrix, then we ensure that all trajectories of the system converge to the kernel of A, which is N, and therefore we achieve the desired formation. So in order to make A bar a stable matrix, we design the gains by solving the following convex optimization problem, which I'm going to explain. So here, in the objective function, we have sum of a square of Frobenius norm of all the upper triangular terms in matrix A bar. So this is sum of a square. The best minimum that we can achieve is 0. And what we are essentially trying to do here is to make A bar a lower triangular matrix by making all the upper triangular terms 0, such that the diagonal terms of A bar are strictly less than 0. And as you know, the eigenvalues of a lower triangular matrix are its diagonal elements, so this ensures the stability. And we want x star to be in the kernel of A in the last constraint. I have to mention that whenever I'm referring to lower triangular or matrices, I mean lower block triangular, and these blocks are 2 by 2 blocks. Or when I'm referring to terms, I mean these blocks. But it turns out, because we constrained the gains to that specific format, all the results hold for the block case as well. So from now on, I'm going to drop the term block and just simply refer to these matrices as lower triangular. The first theorem that we have says that if the minimum is 0, which means that we have successfully made A bar a lower triangular matrix, then the desired shape is achieved. Everything converges to the kernel, and that's the desired formation. And the second theorem, we've given sufficient conditions under which we guarantee that the minimum will be 0, and it's in terms of number of gains, which is a function of number of edges that we have in the graph and number of agents. And what this inequality is telling us is that we need to have sufficient sensing in the topology. So for example, a disconnected graph will never satisfy this inequality. So going back to our example, we had these 3 agents. At this desired formation, we defined vectors x star, and then we form N from 1 bar, x star, and x star bar. We find SVD of N. From that we extract Q, and then we define matrix A bar. And in this simple case of 3 agents, it turns out that A bar doesn't have any upper triangular blocks, so the objective function is trivial. However, we still have the constraints, and notice that these are linear constraints in terms of the unknown gains. This is a convex problem. It can be solved very efficiently and very fast. And starting from any random initial guess for your solution, you're guaranteed to converge to a global minimizer. We use CVX in MATLAB to solve this problem, and the set of gains that I showed you earlier that stabilize the formation, they actually came from solving this problem. So now let's talk about the dynamic topologies, and let's design the gains for this case, for the dynamic case. So here I've shown an example of all feasible undirected sensing topologies among 4 agents. There are 10 of them. And the reason that I've shown this for undirected topologies is because for directed ones we have more and it becomes hard to illustrate them all. But the method works exactly the same for the directed case. So now let's just focus on topologies 1 and 2. And notice that agents 2 and 3 have the same set of neighbors. However, agents 1 and 4 have different neighbors because 1 and 4 are not connected in topology number 2. So since agents do not communicate any information, from the point of view of agents 2 and 3, these two topologies are the same. They cannot distinguish between them because all they know about the topology is their neighbor sets, and they're all their neighbor sets are the same in these two topologies. However, agents 1 and 4 can distinguish between these two topologies because they have different set of neighbors. So whatever set of gains that we come up with that stabilizes topology number 1 to the desired configuration, we need to make sure that we use exactly the same set of gains for agents 2 and 3 in the second topology because they cannot distinguish between them. However, we are free to choose different gains for agents 1 and 4 to get to that desired configuration. And having that in mind, we now solved a slightly more general convex problem, where now for each topology, we have an A-bar matrix and we distinguish them with the superscripts K. And what we're trying to do here is to simultaneously make all those A-bar matrices lower triangular such that their diagonals are strictly less than 0 and therefore stability, and X star is in the kernel of A, so we converge to the desired configuration. And this is what I just mentioned in the last slide, that if for two topologies K and L neighbor sets of agents I are the same, then we need to make sure that the associated gains are equal. So if the minimum is 0, then the desired shape is achieved for an arbitrarily changing topology. And I'm sure you know that if you have two stable linear systems and switch between them arbitrarily, the overall behavior can be unstable. However, this does not happen here because of the triangular structure of these A-bar matrices. And there's also the sufficient condition given in the paper, which ensures that the minimum will be 0. It's in terms of number of edges, number of topologies, number of agents, and number of non-identical neighbor sets. And for more details and proofs, I'll invite you to read the paper. Lastly, we consider fixing the scale of the topology by augmenting the linear control law with this nonlinear term, where f is an odd function which is positive for positive x, negative for negative x, and is bounded. And dij is distance between agents I and j, and dij star is the desired distance. And what this term is trying to do is to push and pull or pull agents such that they converge to the desired scale. This dynamic leads to this matrix vector representation where all the nonlinearity can be lumped into this capital matrix F, which has the same Laplacian structure of matrix A. Therefore, it can be thought of as a perturbation in non-zero elements of A, and if this perturbation is small enough, then we ensure convergence to the desired formation locally. However, this nonlinearity can induce or introduce undesired but perhaps unstable equilibria, and that's something that we haven't analyzed in the paper, and that's a topic for future work. Lastly, I want to show you a simulation with 4 agents starting from a random initial position on the plane. The desired configuration is a square, and as you can see, the topology is switching randomly according to this graph among all these 10 feasible topologies, and regardless of all the switches, the agents achieve the desired formation. With that, I want to thank the programs that supported this work, and thank you for your attention. And if you have any questions, please feel free to send me an email. Thank you.